All right. Well, welcome everyone, and thank you for joining us for today's fourth and final webinar in our Hydropower Insights webinar series. My name is Angie Furman, and I'm the River Training Center Coordinator for River Management Society. We'll be helping out, following along in the chat today. Reach out if you have any technical questions, but really excited that everyone's here. This series is really diving into the basics of hydropower projects, hydropower's role in the energy market, its role in providing ancillary services to the grid, and trends and changes in the licensing process over the last 30 years. So we're hoping that experienced practitioners and new practitioners alike will have learned from these sessions and leaving you better poised to navigate the complexities of hydropower projects in the licensing process. So just a quick mention, this series does build on the foundation laid by the Hydropower Licensing 101 Toolkit. This was a project published last year by River Management Society, the National Park Service, and the Hydropower Reform Coalition. And this four-part series is designed to address some of the gaps in available resources that we found. So I'm going to put a link here in the chat to this toolkit where you can check out more. I'll also put a link here soon to our hydropower playlist where you can check out any of our previous sessions. We've been recording all of these, so you can go back and check out any that you may have missed. So today we've got hydropower's role in the energy grid. Just a few quick reminders. We're going to be using the chat here. So if you have any questions, feel free to put them there. We'll also have some time at the end for Q&A, where you'll be able to come off mute. Use that little reaction button to raise your hand, and then we can call on you, and you can come off mute. And also, we do have closed captioning available, and we are recording this session, as I mentioned. So with that all out of the way, let's go ahead and get started. I'm going to pass it over first to Abhishek Somani to introduce himself.
Good morning, everyone. Thanks for inviting us, and a pleasure to be here. And my name is Abhishek, and I'm at Pacific Northwest National Laboratory. I'm an economist by training and with background in power markets, electric power markets. I manage and oversee some of our hydropower research at PNL, which is looking at hydropower's role in the power system currently and as it's likely to evolve in the future. A lot of this work is funded by the Department of Energy, and I also represent the Department of Energy in some of the International Energy Agency work related to hydropower. So thank you. Thanks for inviting me.
Thanks, Abhishek. And now I'm going to pass it over to Hill Balliet.
Thanks, Angie. Great to be here. My name's Hill Balliet. I'm the the group lead for energy and water systems analysis at Idaho National Laboratory. Most of my work is in economic valuation of hydropower, particularly adding batteries to hydropower plants, looking at increasing revenue and those sorts of things. We also work on operating those hybrid systems, developing controls for them, and economic assessment for energy storage devices in general.
Awesome. I'm going to go ahead and stop sharing my screen, and Hill, you can.
Thanks. Let me pull up my slides. All right. Can you all see this?
Yep, looks great.
All right. So I want to talk today, give a little bit of an introduction about hydropower's role in the grid, and then talk about black start a little bit deeper. And we'll get into what that means for anyone who's not familiar. So to start things off, I want to clarify a little bit about base load versus flexible operations. So base load is the minimum load on the system in a day, and you can kind of see on this right graph, I've broken things out by what is base load and then what is peak load. Some people will characterize an intermediate load as well, but these are kind of the two important distinctions. And the reason that these are important to the grid is that there are a lot of assets like coal plants or nuclear plants that have very low flexibility, but they have cheap bulk electricity. And so generally what they'll do, and what some hydropower does as well, is contribute to this blue section of the graph, giving kind of a flat output throughout the entire day. So that's one way hydropower can be operated, but it can also be operated flexibly to try to match the shape of the peak load. And this provides a lot of value to the grid because not everything can ramp. And generally the faster that assets can ramp and follow this peak load, the more expensive their power is. So think, for example, natural gas versus coal plants. Natural gas plants are very flexible, but they can be more expensive when you're trying to operate them to meet these peak loads than like a nuclear, coal, or solar plant that might not be quite as flexible and responsive. For hydropower, they can be operated either for base load or flexible generation. Some plants have the capability to do both. Run-of-river plants generally have less flexibility and are often just operated for this base load. But whether they contribute to base load or flexible generation depends in general on inflows, reservoir size, and plant components. Components can limit the speed of ramping. They can kind of force plants into operating in base load, but generally upgrades can be done to modernize the plant and improve its flexibility. So a few types of flexible operation. Following hourly load demand. So that's kind of following this peak load, ramping up and down to provide the most value to the grid. Frequency regulation. So if a load or a generator comes offline or online very quickly, then trying to balance that power out on the grid is important. And then also responding to real-time prices if you're bidding into a market can also be another type of flexible operation. So that would be ramping within the hour, often on 5-minute intervals. So diving into some of the grid services that hydropower provides, one of the biggest one, which is generally compensated the most in power purchase agreements and in markets, is energy. So the amount of megawatt hours provided annually, independent of when they're provided, is typically compensated and is most of the value that's derived from a lot of energy generation devices. Capacity is a little bit of a distinction here. So rather than looking at how much energy is being provided regardless of timing, it's looking at how much energy are you providing when it is needed most. So if you look at the peak demand hour of the day and you look at how many megawatts are being provided during that peak hour, then you can get a sense of how much your hydropower plant is contributing to resource adequacy in the area and how much firm capacity it's providing. Ancillary services, I talked a little bit already about frequency regulation. So ramping up and down to balance supply and demand on very short time scales is an important service that keeps the grid reliable. Providing reserves is also important. We've got 2 time scales of reserves on the system. One is spinning and one is non-spinning. So the cutoff between these two is basically how fast you can respond to a signal to ramp up or ramp down. And so in the case of being a reserve, the plant doesn't necessarily have to be operating to participate in reserves. It'll just be on standby to respond to signals from the grid operator. Reactive power is another important service that hydropower provides. This one is somewhat specific to synchronous generators. So that would be, coal plants and natural gas plants and nuclear and hydro. All of those are very good at providing reactive power. And typically inverter-based resources like solar and wind are not as good at providing reactive power to the grid. But this is important because it helps support voltage stability. So active power supports frequency regulation, and reactive power supports voltage stability to make sure that the voltage on your lines stays up at its nominal value. For black start, which is what I'll dive into farther in the later in this presentation. This is focused on starting up the grid after a blackout when the plant has to supply all of its own power required to turn on. So a lot of plants can't do this, possibly because they have to, in the case of a thermal asset, they have to heat up significantly before they can operate and add power to the grid and be efficient. And so they need a large power injection before they can supply their own power, or for some other reason they can't necessarily get started without power. Hydropower plants are really good at this because they have, they're synchronously connected to the grid, so they provide inertia, which helps stabilize the frequency on the grid. And they provide all of these other services, and they can be, flexible in a lot of cases. Black start can be split up into two different types. One is transmission level and one is distribution level. Historically, transmission level black start has primarily been how black start is done. There'll be large centralized generation plants that provide black start out on transmission lines, and the grid is started up that way. Distribution level black start is relatively new, and we'll talk about an example of that here in a minute. So breaking down hydropower capabilities by plant, both run-of-river and reservoir hydropower plants can provide a lot of these important services, but there are some distinctions between the two of them. So, for example, energy provided by run-of-river and reservoir is limited by inflows in general, but reservoir hydropower can kind of work around, the daily and weekly inflows and save water across seasons, for example, to provide more energy in total, independent of when the rain is coming, because they're less likely to have to spill water during the high flow times, and they can save what would have been spilled for later. For capacity, run-of-river is very much limited by when water is coming in. Reservoir hydropower has more opportunity to be flexible and ensure that capacity is maximized so that power is being produced when it's most needed. For ancillary services, it is limited with run-of-river plants. Some of them have some flexibility to provide ancillary services, but it's very plant dependent, and reservoir hydropower plants are good at providing these. Both types of plants are good at providing reactive power, especially compared to those inverter-based resources. And black start, this is kind of similar to energy. If you have enough water coming through, both run-of-river and reservoir can provide black start, but there are times when there's not enough water available at run-of-river plants for them to provide black start. Another big limitation of providing black start could be outdated components. So, for example, a lot of hydropower plants were built before digital governors were common, and those are necessary to control the plant and make sure that it can be flexible enough to provide black start. So a little bit of the motivation for why people are looking at hydropower plants for black start so much more recently. You know, it used to be kind of crazy that people might shut off transmission lines electively, but this has become much more common since the Paradise Fire, you know, which was caused by an overloaded transmission line. So now, more and more commonly, utilities and grid operators in the West are starting to shut off power lines when there's high wildfire risk to avoid starting fires. And when this happens, communities can get cut off completely from the grid and experience long duration blackouts, which they may want to be resilient to. They may want to be able to recover from on their own without having to be attached to the grid. Another motivating reason why we've seen interest in this. So in Idaho Falls Power, which is our local co-op at Idaho National Laboratory, there was a winter storm which caused a blackout a few years ago, maybe 5 years ago or so, which caused, you know, an emergency because it was so cold and people needed power to stay safe during the winter storm. And so they were really interested in being able to get their grid back up and running, even if there were, you know, transmission line outages in the area that connected them to the larger grid, so that they could, you know, maintain safety for the city. And so based on this interest, we collaborated with Idaho Falls Power to perform a field demonstration showing that their plants were capable of providing black start and that the black start services could be improved by adding an ultra capacitor to their hydropower plants. A little bit of an overview of how black start works. Starting from no load on the system because everything is blacked out, the load is added back on in steps. So little pieces of the grid will be reattached to whatever plants are providing black start. And whenever these steps happen, there's a significant effect on the frequency. I think Abhishek will have a good demonstration of how load and frequency are related. He's got a good illustration that he'll show. And when these frequency drops happen, the generators respond by ramping up the power that they're producing. And if you add energy storage to the hydropower plant, you can minimize these frequency dips while the hydropower plant is taking time to ramp up. You can have short burst injections that help stabilize the grid. So this is a little insight into the type of hydropower plant that we were using in the Idaho Falls Power Field demonstration. They had Kaplan bulb style run of river plants on the Snake River that goes through Idaho Falls. And they were not originally designed to provide flexible power or provide stability to the grid. They're provided to operate efficiently at a steady power output. So we were able to show that adding energy storage improved the response of the system, that they were able to provide better black start when we created an optimized black start mode for their governor controls. And then also by synchronizing multiple plants to provide black start, we were able to get a significant improvement in performance so that they could carry more critical loads. And here's some results. You can see in the bottom graph that when the ultra capacitors were added, the change in frequency after the increase in load was reduced, and the oscillations that happened after recovery were damped. So I mentioned a little bit earlier that one of the things that can limit black start capability is having outdated components. So last summer we did a field demonstration with another co-op. This one was Fall River Electric, which operates in a much more remote area. And so they had a plant that had not been modernized yet that they wanted to see if they could provide black start services with. And so we worked with them to retrofit their plant with a few different components, programmable logic controllers. We replaced an on-off valve with a proportional valve that could provide more flexibility. Added a guide vane and gate position sensor so that we could feed that state back and control the plant better, and a generator speed sensor. And there's some news coverage that you can look at to see more about Fall River Electric's experience with this and some of the technical details in the publications. But we were able to retrofit the plant with kind of a minimal set of hardware to enable them to run without the grid and support critical loads during emergencies. So yeah, I don't know if we want to do questions now or wait until the end, but appreciate y'all listening in.
Thanks, Hill. I haven't seen any come in, so maybe we'll wait until the end. But if people do have questions, I encourage you to put them in the chat. That way we can get to them and not forget them. But if Abhishek is ready, we'll pass it over to you.
Thanks.
All right. Just give me a minute. It's not letting me share just the
program.
right.
Well, that looks good on our end.
Okay. That works for me. All right. It's coming through all right, right? Okay.
Yep.
All right. Thanks. Thanks, Hill. Thanks for actually that set up my presentation quite well. I will not do a deeper dive into all of the grid services because Hill explained that quite well. But I just what I want to concentrate now on is on a specific set of essential reliability services that hydropower contributes towards, and it helps with maintaining grid reliability and resilience. And resilience especially, and if you're defining resilience, this is specifically talking about helping the grid, the system recover after major loss of generation events. So generation resources that are online and suddenly go offline, which those are called unscheduled outages. And the system requires swift autonomous responses to help recover, stabilize, and then go back to normal operating conditions. So that's what I want to be concentrating. And this is based on some work we've done in the past, and we've got some ongoing work as well. So I'll talk a little bit about that as well. The motivation for this work was, this was, I would say maybe 2018, 2019 kind of time frame, and we through the DOE commission workshops, we would hear from owners and operators of the hydropower facilities that they were pretty aware. They know very well how much these attributes and of hydropower are necessary in providing these essential reliability services, but they're not always compensated commensurately. And the main reason it sounded was because these were not studied and quantified systematically, and so that's what we did in this project. We used historical data, and we used simulation tools, and did some simulations to really quantify hydropower's contributions to these grid services across a variety of different timescales. So everything from seconds to minutes, which is voltage support and inertial and primary frequency response kinds of things, to minutes and hours. Although we were mostly focused on the seconds to minutes. The other ones were more data-based analyses, and I'll present some results on that as well shortly. And because of the validation we were able to do of the simulation tools, we're now using those same simulation tools and the processes to understand how hydropower's role might evolve in future as the system conditions change and we march towards our decarbonization goals, and not just under normal conditions, but also under extreme weather, such as heat waves or cold snaps and combined with things. So just to give a little primer on hydropower in the U.S., and this is mostly, our study was mostly focused on the north, on the western interconnection, so the western half of the U.S., and so that's where most of the focus is going to be in this presentation. And just to do some level setting, hydropower is, as you might be aware of, a mainstay of the energy, the infrastructure, electricity infrastructure in the western U.S., but definitely in the Northwest. It contributes anywhere from 70 to 80% of both the in terms of the installed megawatts, but also the amount of energy it generates throughout different years. And that, of course, depends on the water availability conditions, but it's still pretty substantial in terms of the energy contribution from hydropower. So in terms of the other essential, what's known as the essential reliability services defined by FERC, and some of these things were that Hill mentioned before. These services were also well understood in terms of how much hydropower contributes. And here's just an example. The graph it's a little dated, but it shows that hydropower is one of the main contributors to the regulation services or contributions to spinning reserves, and not so much the spin, but definitely some of the other services that are needed to maintain reliability and ensure that the demand and supply conditions are in balance at all times. So this was also pretty well understood, and it just happens to be that these services are also monetized, and so whatever hydropower is contributing, they get commensurately compensated for providing these reserve services. What wasn't known is what I was getting at is those other kinds of services that are especially in the seconds and sub-seconds kinds of timeframes, and these are important to ensure that I've got a little graphic which so the demand and supply in the power grid have to be maintained at all times, and looking at the frequency at which the system is operating is one measure of whether how well we're doing relative to maintaining that demand and supply. So at any given time, this is how the system is operating, and this is what we would call normal operating conditions. The system is never perfectly in balance. There's always the give and take between demand and supply, And that's where some of those essential reliability services that I presented previously come into play. Using those balancing services is basically what helps keep the system, the demand and supply conditions in balance at all times. But what we were really after is these conditions that happen not all the times, but once in a while, when you lose a big chunk of your generation fleet, and that causes major imbalances. And if not corrected swiftly, then that can lead to wider cascading outages throughout the over a bigger part of the interconnection. And so that's what we were really looking for. That's what the investigation in this study was focused on, is how much does hydropower contribute towards those services that help the system recover after these major events. And I won't spend a lot of time on this, but just to give you an idea, we're talking about it's seconds, less than minutes, definitely, but even sub-seconds. And talking about attributes like inertia, which help with inertial response, that help control the arrest, the frequency dropping after these events, and then the primary frequency kinds of responses, which are through the governor's actions that Hill mentioned, that help the system rebound and recover and go back to the stable operating points. So with that, let's dive results, and starting with the data that we had for some of the major events that happened in 2017 and 2018. In that time frame, hydropower contributed comprised about 25% of the installed capacity in the Western interconnection. But our analysis showed that hydropower, especially from the Northwest, contributes anywhere from 30 to 60% of these frequency response kinds of services. And it was pretty interesting to see that the location and the timing of the event mattered a little bit, but because the timing of the event, like whether the event happens in spring versus summer versus let's say winter, depending on the amount of hydropower that's online, but based on the water availability during those conditions, that's when the amount of response from hydropower changes depending on the time of the year. But the location of the event was less significant in terms of the responses that were being provided by hydropower. So suffice it to say, hydropower is and was and continues to be a major asset for the Western interconnection, and provides these essential services at different times of the year. Now, what we were also able to do was carry out simulation studies using some tools that had been put together for this project, and the simulation studies basically showed this similar results, that hydropower is still the single largest contributor towards primary frequency response. But with the simulation studies, we were also able to look at the amount of reactive power that was being provided by hydropower to help with voltage support. And we were able to look at a few different scenarios. First scenario is what's known as the single largest contingency in the Western interconnection. That's basically the two nuclear units the Palo Verde units in Arizona that suddenly go offline and create that massive supply demand imbalance. And the other one was looking at the outage of a natural gas pipeline, which causes sequential outaging, the outage of the natural gas generation plants. So under both of those scenarios, we found again, as we found with analysis of historical data, we found that hydropower is contributing anywhere from 30 to 60% of frequency response. And if you look at the graph on the right, hydropower was the single largest contributor towards voltage support as well. And that's important. And this was just looking at the system as it existed in 2018, and partly as the system is projected to be looking like in 2028. But as we move towards our decarbonization goals and have more inverter-based resources coming online and less spinning mass from decommissioned thermal units, it's going to these services are going to become more scarce and hence more valuable. And that's another reason why it was important to do some baseline analysis of how much does hydropower contribute towards these services. But now we can use these same set of tools that were put together to understand hydropower's contributions presently. We can start using them, and we have been using them to assess what from hydropower in future, and let's say in a 2035 grid with 80-90% decarb under different kinds of system stresses like heat waves or cold snaps. And that's what we're working on presently, looking at the can you still see my screen?
Yes.
Okay. Yeah, so that's what we're doing presently. We're taking the same framework and the set of the simulation tools that we've put together, and we are looking at hydropower's contributions under different future grid conditions in different combinations of extreme events and under different water availability conditions as well. I think that's what I have. Yeah.
Thank you, Abhishek. All right. We have some time for questions, and I saw one just come in, and I'll read it out. Jack, also, like if there's someone in particular you're hoping would answer this, feel free to speak up. But it reads, when inverter-based assets like solar and wind are paired with energy storage, can they then provide reactive power, black start capability, frequency reg, and other ancillary services on par with synchronous generation assets like hydro, coal, gas, nuclear?
Yeah, I mean, the short answer is yes, but it depends on the the kinds of controls that we have in place, and then because what this requires, providing these services requires, is maintaining some amount of capacity, some headroom, so to say, that can be used to provide ramping up, ramping down kinds of services, regulation up. So energy storage does definitely help, right? It adds capacity at with those resources to be able to provide those services. But these resources, and it's actually been done in field demonstrations with solar plants in California, that they're just as capable of providing, with the advanced controls and the right kinds of technologies, that they're actually able to provide these services themselves. But again, that requires curtailing some amount of renewables to maintain headroom for providing these services.
I'll just add one thought to that. I agree in general from, probably like around, half a second upwards. I think as we get down to like the inertial time scale, we're not quite good enough at controlling them yet to ensure that we're maintaining stability and we don't cause issues when faults happen and that sort of thing. So I don't think that the extremely fast time scale contributions can be emulated yet. That may be coming in the future, but it hasn't been applied yet.
Thank you. All right, I see another question from Andrew. Is the study on hydro's role in grid services also going to evaluate changes in revenue or recommendations on policy to support any projected need? And is it relevant for other US regions?
So not in that study itself, but we have a different study that we work with Argonne National Laboratory. We collaborate with them, and in that study we have looked at how the revenues from different services might change based on different future system conditions and things like that. So we still don't have a good way of monetizing the value of things like inertial and primary frequency response. There are certainly examples from other parts of the world. In the UK, for instance, they have an actual market for inertial response now and primary frequency response. So we can take some cues from them, but we still don't have it in the US at least. Apart from ERCOT, ERCOT has a something called a fast frequency response service that they have put in place recently. But in other parts of the US, we still don't have that those services monetized presently.
And then a follow-up question to that, is there a way that you can maybe send a link to that Argonne study, or if it's hard to
Absolutely.
look up now, you can always send it to me and I can send it out along with the recording to everyone.
Yeah.
Awesome, thank you. All right, another question, this one from Steve. Hydro is obviously useful. Is it essential? Can battery storage replace the capabilities hydro has over inverter sources on the grid?
I'll take the first crack at this one. So there are a lot of ways we can achieve a reliable, clean grid. The issue is trying to pair in affordability with reliability and decarbonization. So, expanding transmission lines significantly, adding tons and tons of new transmission lines would have a really big impact towards reducing the need for synchronous generation and those sorts of things. The issue is feasibility. Getting permits and making it happen is almost impossible. So that can't solve the problem on its own. Adding way overbuilding renewables is another way to do it. That's extremely expensive. Adding a ton of batteries is another way to do it. The issue right now is that really the only economically viable way to add batteries is about 4-hour storage. That's what we're generally seeing right now. As technologies get better with hydrogen storage, thermal storage, and compressed air and things like that, maybe we'll see much longer duration energy storage devices that can start to replace some of the contributions of hydropower. But really, hydropower right now is providing some services that are extremely expensive for us to provide any other way. It's providing inertia. It's providing, especially large reservoir hydropower plants are providing the flexibility to save energy across seasons and to save energy for solar droughts and wind droughts when there's maybe a week at a time, when there's very low variable renewable generation. So if our goal is decarbonization has to be reliable and affordable, I would say hydro is very important to that.
And I can present a slightly different perspective on that. And I agree with everything that Hill said. But what we're seeing in different parts of the country is that hydro is providing these services, but in providing these services, they're operating way differently than they were designed to operate. So there are examples from resources participating in the energy imbalance market in the West, or resources participating in MISO markets, and they're providing these balancing services, which are becoming increasingly more important as the penetration of renewables is increasing. But that's what that's doing is also putting more stress on the machines and the different components, and that's where we've seen some pairing with batteries can really help, so that they can continue providing those services and avail the business case, which is by providing all of these grid services. But the batteries can basically take bulk of the work of being yanked around, as opposed to the machines doing that and taking the stress away from the machines. So I mean, is it essential? That's a very good question. Like, Hill said, there are a lot of different ways of addressing like how we get towards the decarbonization goals and how to meet those grid services. But presently, it's playing a major role, like we've seen in these different studies.
Yeah, thanks. Good answers. I just, I guess my response is it sounds like it really is, not completely essential, but right now it'd be extremely expensive to implement alternatives. I guess just looking forward, is our hydro infrastructure continues to age, and as battery storage capabilities continue to evolve, that situation could change. So anyway, thank you.
All right. Next question comes from Bud asking, from the standpoint of homeland security, how does hydro compare with nuclear or solar as risk if the US came under drone attacks? Or any thoughts on risk?
This is not one of my areas of expertise.
Not mine either. But I'll give you a little anecdote that I heard from someone else doing cybersecurity work and specifically looking at hydro. And given that these resources, like Hill said, didn't have digital governors and didn't have AGC kinds of controls put in place, because they were operating in a different paradigm altogether. So they didn't have telecommunications infrastructure, right? The way we have them for other modern plants. But now that a lot of these plants are joining markets and they have to have those controls in place, that's when the telecommunications elements are getting added at these facilities. So when we first asked, or when people first asked this question of cybersecurity, is there a cybersecurity risk? The answer was, what cybersecurity risk? Because we don't have the telecommunications, the infrastructure at a lot of these facilities. But this was again a little dated.
Thank you. And then Stefan asks, are either of you looking at the grid services and contributions of hydropower under various scenarios broken down by specific hydro projects within the Northwest?
Yes. What you guys? And I can elaborate a little. So the study, the results that I presented were at the aggregate level at the fleet level, but we can absolutely break them down, and we have done that and looked at the contributions from individual facilities under those conditions, both with historical data, but also with simulation, because it's a very highly resolved model of the Western grid. So we basically have each and every plant represented in that model, in those models. So we can absolutely, we have done that. We have looked at what individual plants' contributions were towards these different services.
All right, another question coming in. This one from Jack asking, if a hydro peaking plant does not have a digital governor, is it completely unable to provide any form of black start services, either transmission or distribution level?
I would say I have not heard any plants that can provide black start without digital governors. Um, those are not extremely expensive to retrofit at the plants. So for the Fall River Electric demonstration that we did this past summer, I think it was maybe I want to say $50,000 about to retrofit the entire plant with the new sensors and governor. So it is something that's not a huge investment compared to the rest of the infrastructure.
All right. Another question from Bud saying, hydro dams have half-lives due to sediment. Would stricter rules on non-point farm erosion extend the life of hydropower facilities?
That is not an area of my expertise, so I don't think I can comment.
Yeah, unfortunately, I haven't studied sediment buildup either.
All right, I'm seeing some questions. It slowed down, so we do have a little bit more time for questions. So while you're thinking of them, brainstorm, write them in the chat. In the meantime, I am going to share a link to a survey, and we would love to hear your thoughts about today's session. Especially as we look towards doing future webinars around hydropower. Would love to hear any thoughts that you have about topics that might be of interest, or where you might still have some questions. So please share your feedback with us. All right. Let's see. If anyone also wants to come off mute and ask a question, you are welcome to do that. I know sometimes writing out the question can take a few minutes, so. All right. Giving it that extra moment of silence. Well, first, I just want to say thank you again so much to Abhishek and Hill today for joining us and sharing all this information with us. I know I've learned a lot, and might have to come back and watch this presentation again just to fully understand. But if anyone else also wants to come back and watch the presentation, I will be sending out the recording by tomorrow midday, and any links or anything that was shared in the chat as far as resources. So I don't see any other questions. And so I think I'm just going to go ahead and give you all some time back in your day. Thank you again, and I hope you all have a great rest of your week.
Thanks for having us.
Thank you.
Take care, everyone.
Thank you.
Good job. Thanks.